Good morning, guys. Dr. G here. I'm getting some emails about what to expect for your first exam, so I think it might be time to do a review video. Your first exam will be available to you from next Monday, February the 6th, to next Saturday, February the 11th. You can come to the TCC Testing Center. You need to bring your ID, and you can come and take the exam. If you are not within Wakulla, Gadsden, or Leon counties, yours will be at a proctored site that you need to set up, so make sure you're getting that ready. What you can expect for the test, I won't ask you stuff that we haven't done, so I'm not going to ask you random stuff from the book that have not been in a homework assignment or on the PowerPoint slides. So those are the two things you can really focus on as you study for this exam. And we're going to walk through some of the main concepts right now to make sure that you understand the main material that I think is important. Okay, so basically we looked at our solar system forming, our Earth forming, the structure of the Earth. We looked at minerals and rocks, and then we looked at plate tectonics. So let's walk through a few of those. We think that our Earth formed around 4.5 billion years ago, and we think this based on examining meteorites to determine the age and what it might have been like. And what we think happened is that there was a large cloud of gas and dust, this is called a nebula, and that something happened and caused it to begin to contract together, so it was gravitationally contracting. Most of the mass moved into the center and became our sun, and that gravitational energy converted to thermal energy. The sun ignited, and it was very hot in towards the sun. It's still very hot in towards the sun. The mass that was surrounding the sun was a very small mass, but it became our planets. So our inner planets formed in a warmer temperature. They're called our terrestrial planets. And our outer four planets, those are our Jovian planets, and those have different properties than our inner planets. So let's talk about our inner planets. Those, because of the higher temperature, ices couldn't condense close in. Only rocky minerals and metals were able to condense to form those planets. So those planets are smaller because they're just made of rocky material and metals. They are dense, and they tend to be made of rocky materials, right? The outer planets, it was very cold out there. So not only did you get the rocky stuff forming, but you also were able to condense a lot of ice. So you have a lot of hydrogen and helium that was able to either condense into an ice or be collected as gas. So those planets are really large. They have a lower density because of the hydrogen and the helium. And they tend to have large atmospheres. And I don't know if I said it, but they're very low density. All right, so those are the planets out there. Large, low density, ice and gas, big planets. Okay, so that's our basic solar system structure. Inner planets, terrestrial, outer planets, Jovian. And we learned about this by studying meteorites. Those are some of the main points I want you to know about our solar system formation. Okay, so then we move on to minerals. And I've gotten some questions about how do you identify cleavage, how do you identify some of the other mineral properties. So let's talk about what I really want you to know. In order to actually identify some of those properties, you'd really need to physically look at the mineral yourself. I know there are some activities on your homework that ask you to look at that, and I wanted you to get practice seeing it, but I'm not going to test you on that. That's something you would really have to have it sitting there in your hand to get good at it. So what do I want you to know? Well, I want you to know the definition of a mineral. Minerals are naturally occurring inorganic crystalline solids. They have a definite chemical composition, right? Meaning you can write the chemical formula of it, and they have specific properties. Okay, so make sure you know that. Make sure you understand what some of the different properties are. I won't ask you to identify them, but make sure you know what hardness is. Make sure you know what the streak is, what the streak color is, what the luster is. That's how light reflects off of it. Make sure you know that cleavage is how the mineral breaks, and the crystal structure is how the mineral forms. Make sure you are familiar with those. And then the basic rock cycle. You need to know that we have igneous, sedimentary, and metamorphic rocks. You need to know how each of those forms. So igneous rocks, you would have a melt, like from a volcano. that would cool and crystallize. So you would have lava, magma, all of those things associated with igneous rocks. Sedimentary rocks, you would break down other rocks. You would weather them, break them down, and so you would have the parts of the sedimentary rocks. And then for metamorphic rocks, you would tend to have a lot of pressure and maybe some temperature, higher temperature, but no melting. So just know the basics of those. Mostly in this section, we're going to talk about igneous rocks. Right? So that's kind of what I want you to know about that. And Earth's structure. Okay, so in your homework, you saw that there was a solid inner core, a liquid outer core. Beyond that is the mantle. Mantle convects because it's hotter at the bottom and cooler at the top. And then beyond that, you have the crust. Okay, so you've got the core, the mantle, and the crust. The core is made mostly of iron and nickel. The mantle is made mostly of iron and a little bit of magnesium. And the crust has a lot more granite type material. It has a high silica concentration. Okay, so iron rich as you go down, silica rich as you go up. That's our basic structure. And that solid outer part actually breaks into plates and moves around. So because the mantle convects, or basically boils, it boils and it pushes this solid stuff on top of it around. And so it's moving around. And these plates are called lithospheric plates, and they contain the solid crust and a little tiny bit of the liquid mantle. Okay, so or a little tiny bit of the mantle, let's say. So they're moving around, and as they move around, they interact with one another. And this is how we get plate tectonics. When they move towards one another, you get two plates coming together, and when that happens, one plate can go under. If one plate is more dense and goes under, it dives into the mantle and it can melt. Okay, so as it goes under, you can get a lot of earthquakes, even deep earthquakes. As it melts, that melt can rise and you get volcanoes above it. So this plate, imagine it's got some silica in it, and it goes down and it melts and rises. You get silica-rich volcanoes that are really explosive coming out. We call those stratovolcanoes. And you saw that in your video. So you see very dangerous stratovolcanoes all around these subduction zones. And that happens, the Ring of Fire is a good example of that. So you get that all around the Pacific. Go back, take a look at your video, and take a look at that homework to review that. But that's one type of plate motion, is the plates come together. That's called convergent. If they come together and one goes underneath the other, it can cause earthquakes, melt, and volcanoes. Okay, so that's at subduction boundaries, convergent subduction boundaries, and those are the most dangerous boundaries. Plates can also come together, and if they're the same density, then they just end up pushing up, and you get mountains. That's how we got like the Himalaya mountains, the Alps. That's how at one time we got the Appalachians. So you get plates coming together and pushing up. All right. The other way plates can move, instead of coming together, they can move apart. So if plates move apart, that is called a divergent boundary. When they diverge, then you actually have the mantle melt rising up to the surface. Remember that mantle was iron rich. So if you get iron rich melt rising up to the surface, then you make new ocean crust. So on the crust there's two types. There's continental crust, which is silica rich, and there's ocean crust, which is iron rich. You make this iron rich crust by having the iron rich mantle melt and rise up. As it solidifies and moves apart, that's how you get ocean crust. Then if the ocean crust moves over to hit a plate at a convergent boundary, it subducts because it's more dense, like we just said. Earthquakes, volcanoes, dangerous subduction boundary. So that's how you get that. Okay, so far we've had convergent and divergent boundaries. Our third type of boundary is our transform boundary, and this is when the plates just slide past one another. If they are just sliding past one another, you get transform. It's a transform boundary, and you get very shallow earthquakes. They can be dangerous, but they aren't going to be the deep earthquakes that you get with subduction. They're shallow earthquakes as the plates slide past. You don't get any new crust forming. And a good example of a transform boundary is in Southern California, all along in that area. San Andreas Fault is actually one part sliding past the other, and Southern California is actually sliding north, and so eventually would slide all the way up to Alaska. Okay, so examples of the three types: the convergent subduction all around the Pacific Ring of Fire. So Alaska, Central America, all along, and then around over into Asia, you get Japan, and all around there. So that's the convergent subduction. Convergent can also form mountains, and that's the Himalayas, Alps, places like that. Divergent, that's the mid-ocean ridges. That's how you get those mid-ocean ridges and new ocean crust forming. Transform, a good example is the San Andreas Fault. So those are your three types. And finally, when we get earthquakes, we get P waves and S waves. P waves are the primary waves. They travel faster, and there you can think of them as P, primary, push-pull. Okay, so this is the material moving back and forth, push and pull. So it can travel through solids and it can travel through liquids. S waves are secondary waves. They travel slower, and think of it as making an S shape or a shear shape. That can travel only through solids. So those are the two types of waves. We record them. Take a look at your homework for how we record them. Basically, we record the shaking of the waves, and we can determine how far away an earthquake is. I won't ask as much on that, but I do want you to know what P waves and S waves are. And the very last thing, continental drift hypothesis versus plate tectonic theory. Okay, so recognize that how we started to learn about these plates moving around, because this was a pretty crazy idea at the time. Most geologists actually didn't buy into that idea for a long time because we don't feel the earth moving under us. We sit here and it feels solid, and mountains look like they've always been mountains, and continents seem like they've always been in the places they've been in, but in fact they haven't. They've moved over time, and so it took quite a bit of evidence for us to change our mind about that. So take a look at how we came up with that information and what pieces we put together. Look back at your homework. There's some good information in there for that. All right. So those are the main things that I want you guys to know. How our solar system, how and when our solar system formed, inner versus outer planets, and why they're the way that they are, the Earth's structure and what it looks like, minerals, their definition and properties, and how the plates on the top of the Earth move around through plate tectonics, and what that looks like and what the different boundaries look like. Okay, I am monitoring your extra credit discussion board. When I see a lot of answers go up, I go ahead and clarify a question. If you have something that you need to know right away and you don't want to use the discussion board, just email me and I'd be happy to answer your questions. Make sure you take your exam between February 6th and February 11th, very important, and your homework is due this coming Monday, which is February the 6th. Okay, if you have any questions, email me. Good luck, guys, and I look forward to looking at your homeworks.